Hello everyone, welcome to our video lecture series on HYSYS and UNISIM simulations, and these lecture series have been organized by www.Unitoperation.com, and today's topic is simulation of a distillation column using HYSYS and UNISIM. You know, these two softwares are almost similar, very similar. In fact, if you know either HYSYS or UNISIM, you should be able to do the simulation on the other one. And my name is Shekhar Bhattacharjee. Distillation is a very unique and important unit operation of chemical engineering. We all learn the design of a distillation column or the simulation of a distillation column using the very basic methods like for binary operation, Mac-Thiele method, and all the way to very complex operations where we can go for multi-component distillations involving several components. Sometimes it could be even 50, some 70 different components. And these are, of course, very much of industrial importance. To very simple binary operations, of course, could be done easily. But when it comes to multi-component distillation, they become very difficult. But there has been extensive amount of research work have been done on the simulation of distillation column, and these have been reflected in the ease and the accuracy by which you can simulate this distillation columns using any one of these softwares. So, without wasting more time, let's go for the very first problem here. Let's see. In the very first problem, this is a very classic problem. A mixture of liquid stream containing 70 mass% of benzene and rest toluene, that means of course 30 mass% of toluene, is fed into a multi-stage distillation column, which is right here. So this is my feed here, where we have 70 mass% of benzene and 30 mass% of toluene, and there are 15 trays, so this distillation column contains 15 trays here. So 15 trays here, and it is equipped with a total reflux condenser. So this is my total reflux condenser. So this is my condenser. So all the vapor which comes out becomes totally condensed and gets accumulated in this reflux drum. And as you know, part of it goes into the reflux, back into the column, and the rest is taken out as a distillate. The feed flow rate is 1 kilogram mole per second. Now here it is mole per second. So this is my feed flow rate, 1 kilo mole per second at 30 degrees Celsius. So this is the feed condition, 30 degrees Celsius and 1 atmosphere pressure. The feed enters the column at the 7th tray. So this is entering at the 7th tray, and there are a total number of 15 trays in the column. The condenser and the reboiler at 1 atmosphere. So this is the atmospheric column. Of course, the column is atmospheric, and the condenser and the reboiler both operate at 1 atmosphere pressure. The reflux ratio is 3. So this has been defined already, and the distillate flow rate has also been defined. So this is 2700 kilomole per hour. So this is the condition, and we have to simulate this particular distillation column. That means what are the different flow rates here, what are the flow rate here, what are the different compositions, and of course the performance of each tray, what will be the compositions of this component in each tray. So you can do everything using this particular simulation method. So with that, let's go to our simulation procedure. So the very first thing what we do, we go open a new case, and here first we go to the fluid package here, and we add the fluid package, and according to this problem, as you can see, we have to use Peng-Robinson equation of state. So we go here and we choose Peng-Robinson equation of state, and then we choose the two different components. The two components are of course a very classical one is benzene, the other one is toluene. So we go here and we choose the two different components. So we go here, we put benzene, and of course then we go for toluene. So these two components have been chosen, so we just cross it out, and of course Peng-Robinson has been chosen, so we can directly go into the simulation environment. So we go here, and the very first thing we do, we choose a distillation column. So this is my distillation column, and there is another method of doing this distillation which is called shortcut method of distillation, which we'll discuss later on. But here we'll go for the standard distillation column, which is right here. So in this distillation column, so by default it comes as T100. So we click here, and the feed stream, we call this as a feed stream. So we write down this one as feed, and here this is a total condenser. So there are so many different options for different condensers. So this one is a total condenser. That means all the vapor which comes in gets condensed here and comes to the accumulator, and part of it goes as a reflux and the rest of it goes as a product. So this is a total condenser. So we write this one as a distillate, and we write this one as the bottom. And we write this is a Q condenser. This is the condenser load, heat load, and this of course the reboiler heat load. So Q underscore reboiler. So once that's done, you click anywhere, and then of course this next comes in. So remember, the stage numbering is done right from the top down. Right here you see this is shown as a default 10, but we will change it because our number of stages is of course different, not 10, and we'll do that little later. So here we have defined the feeds, and we have written as distillate. This is the bottom. This is the Q condenser, Q reboiler. So we go to the next window here, and here's the condenser pressure. We know that this the condenser as well as the reboiler working at 1 atmosphere. So we put here 1 atmosphere pressure. And here also reboiler, we are assuming no pressure drop to start with, so we just write down as this 1 atmosphere pressure. So once that is done, and we are assuming the condenser pressure drop is 0 by default. So let's go to the next one, and here we have the optional condenser temperature. So this is optional. That means you can give it, or if you give it, that will be taken as a first guess. If you don't give it, then it will take it on its own. So since this is optional, we'll just ignore this one. So we go to the next, and then here you see the reflux ratio. According to this problem, the reflux ratio is 3, and the distillate flow is 2700 kilomoles per hour. So this reflux ratio is 3, and this is 2700 kilomoles per hour, which comes out of course as a liquid. So we go here and we put here the reflux ratio is 3, and the liquid rate which is coming out as a distillate, which is we put as 2700 kilomole per hour. So once that is done, so all the parameters have been defined, so we just click on done. Now we come here, and here as you can see, according to the problem definition, it has 15 trays, and the feed is entering at the 7th tray. So why not we do that? So we put here as 15 trays here, 15 trays. So this is the number of trays in the column, and here the inlet state. So here we put as 7. So at the 7th tray, the feed is entering this distillation column, which is 15 number of trays. So once that is done, we have defined the connections. So let's go to the worksheet here, and now first if we define the composition of feed of course is 0.70. We go here, but the 7 is the mass fraction, because if you can see here it says 70 mass percent of benzene, not mole percent. So here we put here mass fraction 70, so this should be 0.7, and this should be of course rest, that would be 0.3. So the feed composition has been defined. So once that is done, we'll define the feed temperature and the pressure. According to this problem here, as you can see, the temperature is 30 degrees Celsius and 1 atmosphere pressure. That's the feed conditions. So we put 30 degrees Celsius here, we put 30 degrees Celsius here, and 1 atmosphere pressure. So we put here 1 atmosphere pressure here, and then of course we have to define the flow rate. And according to this problem, the flow rate is 1 kilomole per second, 1 kilomole per second. So we go here and we define this flow rate as 1 kilomole per second. So we here cut kilomole per second. So as you can see, this has already been done. So just for here, you can go onto the design, and you can see here all the parameters have been, as it's given in the problem, have been defined. So this is my feed, this is a 7 tray, and this is a 15 number of trays. If you want to check the monitor, So this is the monitor tab here. You can see the reflux ratio has been defined as 3 and the distillate fluid is 3700. So we have given all the data which are required in this particular problem here. So why not we simulate the problem? You just hit. So right now this is unconverged. So we hit run here and you see this is converged. So the problem has been totally solved. And if you come here, so you go to the worksheet and if you can see that the flow rate is the inlet flow rate is of course 3600 kilomole per hour, because remember it is 1 kilomole per second. So that is 3600 kilomole per hour. So almost 900 would be coming out as the bottom and 2700 is the distillate, because that was the requirement. 2700 kilomole per hour that has to come out. So according to the problem statement, of course, if it is 2700, this is going to be 900. So what are the compositions? So if you go here, you look at the composition. So this would be my composition. So this is my bottom composition. Of course, almost no benzene there. Almost all the toluene, pure toluene at the bottom. And of course, this is 97.74% of benzene in the distillate and very slight amount of toluene at the distillate. And if you see the conditions here, this was of course the feed temperature 30 degrees Celsius. Pressure of course will remain the same because this is an atmospheric column. And here as you can see, this is 110.3, which is pretty much the boiling point, normal boiling point of toluene, and this is 80.62, which is very close to the normal boiling point of benzene. Of course there is a little difference because it is not exactly pure benzene. So that's the way you do it. And then of course if you go to the parameters, then there will be a lot of you can see the pressure and the temperature at each stage, and the liquid flow rate, the vapor flow rate, and later on we'll show you how we can get all the design parameters. You can also define the efficiencies at each stage. Then you can do the plotting. So we'll show in my later videos when we go into little more complicated problems how to do that. So this is my very first problem, and you can just take all the data here. So these are all my conditions, and these of course are the compositions. So why not we go to the second problem? In the second problem, if you see here, so that's my answers given for my first problem here. I have given you the summary. Why not we go to the second problem? In the second problem, if you see that similar the distillation column with the conditions and the specification, with the conditions and the specifications same as given in the problem 1. So all the conditions remain the same as the problem 1, except what is except? That is the distillate flow rate. Instead of distillate flow rate, the bottom flow rate is 650 here. So what we're going to do here, as you can see, everything else remains the same. That means your feed flow rate and the feed compositions will remain the same, what we have seen in problem number 1, and the feed conditions remain the same, and will enter the 7.3, and that will be total number of 15 trays. This would be a total condenser, and this of course would be atmospheric condenser, atmospheric boiler. The reflux ratio will remain as 3, but in the previous problem we had the distillate which was 2700 kilomoles per hour, but in this problem we say no, we don't define the distillate flow rate, we'll define the bottom flow rate. So how do we do that? So for solving this problem, what we'll do, we'll go here and we go exactly to the same problem here. Let's go here and see, you have already given all the data here, but now you have to change the instead of distillate flow rate, you have to go to the bottom flow rate. So for doing that, what you do, you go to the design, and connections of course remain the same. Here you go into the specs. Now once you go to the specs, you see all the column specifications come in here. The reflux ratio is active, so this is the one you have to really keep an eye on. So this is the one you have to keep on. So this reflux ratio is active, so this checkbox you have to keep an eye on. So this will remain active, but the distillate flow rate here, which was active here, because if you see here in the view, if you click on the view, the distillate flow rate view, you'll see that the this is distillate rate, and the draw was the distillate at the column 1, so that's my column, distillate, and 2700. So this is the value we had put in. Now that was my first problem, but now we do not want that. So we want to define the bottom difflux rate. Of course we are not defining, so bottom product rate we have to define. So here if you go there, and what you do here, you click on the view, and view, as you can see, this is bottom product rate, and of course it will be bottom in the column number 1. So this is the column what we have defined, it is coming at the bottom. So here this is the column at the bottom, that's what it is coming in, and this is 650 kilomoles per hour. So that's a total flow rate. So here this a molar flow rate is a basis, and the spec value of course would be 650. So remember, in the problem 1, 2700 was the flow rate. In the last problem here, 2700 was the flow rate here, distillate, so this was like 900. So now we are drawing less of the bottom, of course. See, if we draw the less of the bottom, so this purity of the compound will go higher and higher, and of course the distillate flow is going to be less. So this would be, the distillate flow would be 3600, 1 kilomole per second is equal to 3600. So 3600 minus 650, and that will be of course the distillate flow rate. That comes of course from the material balance. So I put here bottom flow rate, bottom this one, molar 650 kilomoles per hour. So once you do that, so now what are we going to do? You say reflux ratio, of course that will remain active. So this will have only 2 degrees of freedom for the distillation column. So distillate rate, we just check out this one, so this is not active anymore. Reflux rate is not active even in the problem 1, but the bottom product rate which you have just defined, we have to make it active. So there are 2 degrees of freedom that have to be satisfied. So this reflux ratio and bottom flow rate. So once you do that, then you do the reset and you run, and automatically, as you see, the column has converged. And how it has converged, you can see the conditions here. You see that 3600 was of course the feed flow rate, and 650 is now the bottom flow rate which we have defined here. We have defined because that's a requirement, that 650 kilomoles per feed flow rate, bottom flow rate, and the difference is of course is my distillate flow rate. So what are the compositions? The compositions, as you can see, so this of course remains almost as a pure toluene, and this of course is a distillate composition, slightly different from the previous one. And of course the corresponding parameters have changed, and all the design parameters have been changed. Let us go to the next problem here. In the next problem, that is problem number 3, so I have given here all the details in our manual. So in our problem 3, what we are going to see, problem 3 is a little different. In problem 3, what we are going to do, see, simulate the distillate flow rate, distillation column with the conditions and specifications same as problem 1. So all the conditions remain the same as problem 1, except instead of distillate flow rate, the composition of the distillate is specified as 80 mole percent benzene. So now we don't define the distillate flow rate, we don't define the bottom flow rate, we define that in the distillate the composition of the benzene, the composition is such that the benzene mole fraction is 0.8. So how do you simulate that particular column? So if we do that, so let's go back to the column here, and now you have to add. If you do the add, and then you go to the column component fraction, so that's the one you have to add here in the column specification. So here we go for column component fraction, and you say add spec. Okay, and here as you can see, so we are not defining the component fraction on any particular stage, we are defining on a stream. That means on the distillate stream which is coming out. So this is the stream. Okay, and what is the stream here? The stream is a distillate composition we are going to define. And for which component? See here, automatically the component comes in, so this will be benzene. And what is the value here? The value will be 0.8, because that's what it says. If you go to the problem here, you can see that it wants a instead of distillate flow rate, the composition of this distillate is specified as 80 mole percent benzene. So here we go. So we have defined that in the distillate, the composition of benzene, the mole fraction of benzene is 0.8. So once you have done that, now let us go here. So reflux ratio will remain, of course, active. Distillate rate is not active. Reflux rate is not active. Bottom row, which was active before, so we check it out. Now the component fraction, that has to be taken into account, because I said 2 degrees of freedom have to be satisfied. So what are those 2 degrees of freedom? Reflux ratio and the component fraction. So once you do that, so you do the reset and you run. Once you see, you said this has already converged, and if you go to the worksheet here, you see that this is the distillate product, that this is 0.8. That means that the component mole fraction, benzene mole fraction, that is 0.8, and of course toluene 0.20, and correspondingly in the bottom for it is this one. So based on that, you can see what the conditions are. So correspondingly all the conditions have changed, and automatically it gives you the design parameters also. So we go to the design parameters and see how we can define much more, or we can include more complexity into this problem. So this particular exercise, or this particular video series, shows you in a very simple term, in a classical benzene toluene distillation system, we have shown how to input the values for a distillation column and how to define and simulate a distillation column in a HYSYS or UNISIM environment. We'll show you much more complex problem in our future video lecture series. That's for now, and that's the way you do the simulation of a distillation column in HYSYS and UNISIM.